Hello, good morning. There are some seats around in here. You kind of have to, step over people, I guess, to get to them in the middle, but there are plenty of seats this time. There's some down in front here and over on the, okay, everybody seems to be sitting. Let's see. On the sort of logistic front, for those of you who didn't get an iClicker last time, we'll be handing them out this time. I forgot to bring the box with me, but I sent a TA over to get them in my office and bring them back. So we'll do another round of handing out iClickers for those of you who missed out last time at the end of the lecture. The labs will start next week. So if there are any of you who just registered and don't have a lab section, please let me know so we can get you into one. If you need to change lab sections, email me. I'm the one who's taking care of that. They are in a room that I was prowling around this morning, and as far as I can tell, this room is completely unmarked. The room is Wiebold 310, but I didn't see a sign any place that said Wiebold 310. What you have to do is go into the Harper building and go up to the Harper Library, which is no longer a library, but that's what they still call it, and walk to the back of it, and there's a door there. So we'll put up signs to sort of direct traffic so that we don't have all of you wandering around lost and confused like I was this morning. I think that's it for the sort of logistics stuff. Yes? Yes, I will post the first assignment, which is the PDF file, on Chalk this afternoon probably. We were just talking about it and getting it finalized this morning, and I haven't quite had a chance to post it on Chalk, but it will be there. So you don't actually have to go to the lab if you don't want to, but it will probably be much easier if you do, because there's people there to work with and TAs to answer questions. And you can probably finish it in the amount of time that the lab is allocated and just have it be done with, and painless and least resistance and all of that. So they're there to be helpful and encourage you to be. There are some seats here sort of in the middle and here in the front. Okay, so the topic of the class is about how we might be changing the temperature of the Earth. And so the first place to start, if we want to sort of start from the very ground floor, is by talking about what that means exactly. What is heat? So heat is just the motion of the atoms that make up the matter that we're talking about measuring the temperature of. So if you're playing pool, you rack up the balls in the triangle and they're sitting there and they're not moving. If atoms and molecules were doing that, not moving, we would call that absolute zero. That's as cold as they can get. And then you smack them real good with the cue ball, and the better you hit them, if you're trying to play 8-ball, you want them to go every place so you get a chance to get some of them in the pocket. So the faster those are moving, the better that is. And the temperature, you could just add up the average speed of all of the pool balls and calculate the temperature from that. That's sort of what a thermometer does, actually. It sticks in there, and then the fast molecules impart some of their extra energy to the mercury in the thermometer or the electronic thermocouple or whatever, and you can measure the velocity. What you're measuring is the speed, the motion of these atoms. So there are different ways that heat can be kind of moved around. Actually, a really interesting thing about this is that, although you can feel all of the atoms, because you press on this piece of chalk and it pushes back, you can't squeeze it. You're feeling sort of all of the atoms, but you can't feel individual atoms. They're too small. And yet you can feel how much motion all those individual atoms have in just the temperature. And the reason why that's important is because if the motion in the atoms in your skin is too much, then it'll start breaking bonds and you'll injure yourself, you'll burn yourself. And so we have to be kind of aware of this. So even though we can't feel an individual atom all that well, we can feel how fast those atoms are moving in the matter. So the way to move heat around, there are a couple of different ways. Well, let's see, we'll talk about different kinds of heat first, the way that the atoms can move. One is just by sort of flying around, like the pool balls. That's called translation. So for the atoms in this piece of chalk, that's not really such a issue because they're all kind of stuck in place. They're not like the pool balls that they can just fly around any place. They're kind of in this, ordered solid. But in a gas or in a liquid, the atoms are moving around like the pool balls on that pool table. And so that's one of the ways of putting motion into those atoms. Another way of storing energy as motion is vibrations. So we think of a chemical bond. We can think of it as as two weights that are connected together by a spring. So the weights are actually the nuclei, the center of the atoms. That's where most of the mass is. And then the springs are the chemical bond that the electrons create between the two atoms. We'll talk more about vibration in coming lectures because this is real important for greenhouse gases, because vibrations are sort of what we're talking about for greenhouse gases. Anyway, the chemical bond in between those two atoms, it's not rigid, but there's an optimal distance that those for the nuclei to be apart that makes the electrons the happiest. And if you pull them out a little bit, it wants to come closer, and if you put them closer together, it pushes them back out. So it is like a spring, kind of. And so there's energy of that system, those two weights on the spring, sort of bouncing back and forth. That's vibration. And then another way of that energy can be stored in molecules is by rotation. So say you have a 2-atom molecule, you can spin it around. And so that's another way of sort of putting, of storing energy in those bonds. So now, you note that a single nucleus, if you had just a single atom of some gas that wasn't, bonded to anything, you don't talk about rotating that. You think of the nucleus kind of like as a point. You don't really think of it as a three-dimensional thing. It doesn't really rotate, doesn't store energy by rotating in the same way that a molecule that has multiple atoms does. So one thing that's kind of interesting about this is that each mode of motion, so for the translation there are 3 dimensions. And so there's actually 3 different sort of modes of velocity that an atom can have in a gas. It can be moving up and down, side to side, and front and back. It's probably moving in some combination of those, not just one or the other. This particular 2-atom molecule just has one way to vibrate. It has a characteristic frequency, like a note on a piano or something like that it'll vibrate depending on how heavy the atoms are and how big the spring is. But there's just one way that can vibrate, so that's one mode. But if you had a more complicated molecule that had multiple atoms like this, there may be 3 or 4 different ways that this can vibrate. So that may be 3 or 4 different sort of modes of storing this motion in the atoms. And then rotation, there's rotation in different planes. So there's multiple modes of storing energy there. Each mode of motion is like a battery. You can think of it as like a battery. It stores the same amount of energy on average, equal to 1/2 K times the temperature. K is a constant called the Boltzmann constant. And on average, every different way of storing energy stores the same amount, and that amount is directly a function of the temperature right here. So the higher the temperature, the faster those little guys are moving. So the next question is, what do we do? How do we move this heat around? Because we're talking about bringing in this heat energy, which is the moving atoms from the sun somehow through 93 million vials of vacuum where there aren't very many atoms. And then we're talking about getting that energy back out of the Earth again. So moving heat around, there's conduction, which is you put a hot thing next to a cold thing, and then the hot thing gives up some of its heat to the cold thing. So the cue ball is kind of like that. When you first knock the cue ball has a whole lot of energy, hopefully, if you don't, hit it offside and make it fly off into the next table or whatever. And then it hits the stationary balls that are all racked up, and then it gives some of that energy to those other pool balls. And so that's what conduction is. And conduction is not much help for climate science because there's nothing to conduct the heat through between the Earth and sort of outer space. So conduction is good for things in contact, but it won't go through a vacuum. So it's not really relevant to warming up the Earth or cooling it down. Another way of carrying heat is by convection. I know you've heard all these words probably in the 3rd grade or something like that, but it's just good to start and get all on the same page here. And we'll use these ideas. Convection is basically like hot air rises. And when it rises, some cooler air takes its place, and so you're carrying heat around that way. And that, again, is not much use for the Earth because you can't convect energy through a vacuum where there's no gas. The heat is actually carried by the gas. Or you could think of a lava lamp. The hot stuff at the bottom rises up and carries heat to the top. So the heat there is carried by the motions of the whatever the weird stuff is they put in those lava lamps. Yeah?
I don't know if this is a silly question.
Of course not.
But why does hot air rise?
It rises. This is not. How could this possibly be a silly question? It rises because the gas molecules, when they're moving faster, are sort of pushing against each other more strenuously. So they tend to expand. If you have gas in a piston, say, and it's kind of cool, it'll be at a fairly small volume, but you put more energy into the motion of those molecules, and they'll push on the walls of that piston, and they will expand. And so when it expands, it becomes less dense, and it rises. And when it cools, it contracts and sinks again. So that's how a lava lamp works, and it's real important in the atmosphere also. So there's a whole chapter on what happens in the atmosphere that, this is like the central question, that we have to answer first to talk about. So that's sort of the answer to that. And then there's another form of heat which is also important in the atmosphere. It doesn't get heat, to Earth from the sun or from the Earth back out to space, but it's very important within the atmosphere, and we'll talk about it more in the future. It's called latent heat. So this is, it's kind of like invisible heat that's carried by, in this case, in the atmosphere, water vapor. So the way, you can boil water and make vapor, right? But what's, not necessarily so obvious, unless you think about it, is that the liquid requires a significant amount of heat to make the water vapor, the gas. So water at a temperature, the boiling temperature, 100 degrees centigrade or 212 Fahrenheit, the individual, the heat energy stored by those atoms in those molecules is a lot less than the heat energy stored in water vapor, the gas, at the same temperature. So it's no difference in temperature, but it's a huge difference in the heat that it takes to put in there. Just because gases are flying around and they've got a lot more motion than in the liquid. So one way to think about how to demonstrate this kind of transformation is to stick your hand into the steam coming out of a boiling teapot. Don't do it, but if you do, you will burn the hell out of yourself. And it's not because it's all that hot that's coming out. The water that's coming out, the vapor is at the boiling point, so 200 degrees Fahrenheit. You couldn't even cook a pizza in an oven at 200 degrees. It's not that hot. You could keep it warm, but you couldn't really bake it. But the reason why you burn so severely is because the vapor comes out and it hits your hand and cools down and it dumps all of this heat. It becomes liquid and it dumps all of that heat into your skin. And so it's not really heat that you can measure with a thermometer exactly, but it's a way of storing heat and carrying it around that becomes very important in the atmosphere. But again, it's not much use for warming up the whole planet or cooling down the whole planet because there's no water vapor in space either. So it turns out that the way to move heat, you already know the answer, between the sun and the earth is by light. So light it's kind of a property of space-time that light exists. Light is a it's a coupled electric and magnetic fields. And I don't think anybody can tell you why exactly there is such a thing as an electric field in physics or a magnetic field, but they can tell you very in great detail sort of how they work. An electric field is you can measure electrical voltages just with a voltmeter, and it has to do with the charge. So an electron, we write it as E, and it has a minus charge on it. And then a proton, or some other, a bunch of protons that are in the center of an atom, in the nucleus, they have positive charges. So we could write that as P plus. And the electric field is this sort of property of the space that's kind of between these two things that make it so that the opposite charges attract each other. and same charges repel each other. Magnetic field is sort of similar. We call it north and south. And the way it works is you can have a north side and a south side of some, magnet. There aren't separate what they call magnetic monopoles. There's no particle that's just a north particle or a south particle the way there is for the electric field. But you can kind of generate this difference between the north and the south in some object like a magnet. And so the north of one magnet attracts to the south of the other magnet. And again, this is sort of a property of the vacuum of space-time that physicists would love to understand from some kind of first principles why these things are there, but it's not so easy to do that. So we kind of take it as like axiomatic that they're there. And the way that these fields work, they're kind of like almost two sides of the same coin, the electromagnetic field they call it. Because a changing electric field creates a magnetic field. It's called inducing it. It sort of creates it just out of, just as a property of the way these weird phenomena work. And similarly, a changing magnetic field creates an electric field. So you can, the electric field making a magnetic field, this is how electromagnets work. Like they pick up the old junker cars in the junkyard with this huge magnet, and then they set it back down again. It's not a permanent magnet, or else you'd clonk onto the car and you'd never get it back off again. So it's an electromagnet. They turn on the electricity going through, and it's going through a coil. So that's considered a changing electric field. And it makes a magnet. So you lift up the car, and then you flip the switch and drop the car again. And that's how it works because of this interconnection between these two things. Also motors. Electric motors run on this principle. So you've got some permanent magnets, and then you make an electrical magnet by running some electricity through, and it makes the rotor kind of turn this way, and then you switch the electric field, so now it turns this way, and that's how electric motors work. The magnetic field making an electric field, this is how generators work. So you can actually take a motor and just drive it, by I don't know, like a windmill or something like that, and you can get electricity out. You move the magnets relative to each other, and you can get electrical power out. So that's how electrical generators work. Or if you have a pickup on an electric guitar, you've got a magnet in there and a coil of wire, and then the metal string is moving. After you pluck it, it moves, and it changes the magnetic field, and then that gets translated by the coil of wire into electrical signal that you then run into your amplifier and melt some faces and do all of that. So light is a combination of these two fields that sort of couple together in a very special way. So it's analogous to a wave in water. In that it has to perpetuate itself. So the wave in water is not something that you can just freeze and have it sit there, without motion. It has to be in motion because the equilibrium, if there was no energy going in, to be stationary, it would be flat, the water line, right? So the way that the water actually moves in a wave is in sort of circles. Actually, if you put a little floaty thing or some little speck of something that sort of is suspended in the water and watch how it behaves as the wave goes through, there's this sort of circular motion. It looks like the wave is moving. I mean, the wave is moving. It looks like the water is moving. But in a deep water wave that's not breaking, the actual water itself isn't really moving. It's not like translating along the way the wave is. It's just sort of going in little circles like that. And the way it works out is that the way that a little particle of water here is moving, it tends to make the water level go up there. And then the way it's moving here tends to go down there. And so you can't just run this wave at any speed, because if you try to push it too fast, it will break, like a wave at the beach or something breaks. But there is a particular speed, given the size of the wave and the depth of the water and everything, at which a snapshot at one instant will look just exactly the same shape as a snapshot at a next instant, only a little moved in space. So the whole thing, the wave is sort of moving, but the little water particles are just kind of going around in circles. And so there's a characteristic speed at which this thing can be a self-sustaining oscillation. It perpetuates itself. It doesn't change from one second to the next, from one time to the next. The child looks like the parent, so it just goes on. Light waves do a similar thing. But now, instead of water level, we're talking about electrical fields and magnetic fields. So say we had an electrical field, something that you might measure with a voltmeter, a voltage, plus and minus. And we start out at some spot, there's a positive electrical charge, and we're going to make a wave out of it that goes up and down. So plus 1 volt, minus 1 volt, back and forth in this sort of a sine wave. And then there's a magnetic field, north and south. Now, right in here, this is moving. That's a changing electric field, right, where there's a slope here, right? So the electric field is not really changing here at the peak, but here it's changing. So when you have a changing electric field, it makes a magnetic field. So right in this part here, the magnetic field is going to be high in one direction or the other. And then here there's no change in the electric field, so the magnetic field is going to be sort of 0 there. But here you have the electric field is changing again, so the magnetic field is going to get negative. And then right in there, the magnetic field is changing. So the magnetic field changing makes the electric field. So it all kind of couples back to itself. The electric field makes the magnetic field. It's like the energy goes from the electrical thing to the magnetic thing and then back again. It's sort of these two waves that fit together to sort of perpetuate itself in time. So just like the water wave that you take a snapshot 10 seconds later, and if it's not breaking at the beach, it's the same shape as it was before. These light waves are the same thing. They perpetuate themselves. They create, offspring in time, or whatever you want to think of it, that are the same as the parent. So they're self-sustaining or perpetuated sort of oscillations. And just the same way that the wave in the water has a particular speed that it wants to go. If you try to make it go too fast or too slow, it won't work. Light has the same thing as a well-defined speed. At which this trick works. and any other speed it wouldn't work. And so you don't get light that goes faster or slower than the speed of light. Just a property of matter, of the electric and magnetic fields, the speed of light is this sort of fundamental constant of nature. It has a sign c, and it is something like 3 times 10 to the 10th centimeters per second through a vacuum. It's a little slower if it's going through, glass or water or something like that. So it's not a fundamental this is the speed of light in a vacuum, and then it can be sort of tweaked a little bit if you go through something. That's how lenses work. By changing the speed of light, you can sort of change the way the light beams are going, and so there is some variation when you go into glass or water or something like that. But in a vacuum, it's a very fundamental sort of constant of nature, the speed of light. Now, light comes in different wavelengths. In a vacuum, the different wavelengths of light all go the same speed, but you can have sort of long wavelength and short wavelength light. Yes. Yes, electromagnetic radiation. They also use the word radiation to mean like particles, like electrons or particularly called alpha particles that come from radioactive decay. They call that radiation too, and that's totally different. One kind of radiation, though, that you get from radioactive stuff is very, very energetic light. So it's a fuzzy word. It has sort of multiple meanings. But yes, this is all electromagnetic radiation. Yeah, is actually I've had reviewer of the textbook sort of crabbed at me because I used the word light to describe infrared, and he thought that light should only mean visible, and I should have used the word infrared electromagnetic radiation or something like that. I don't know. Maybe he's right. He or she. I don't know who it was. So the kind of light that comes from from cosmic rays that will give you cancer and stuff is very, very short wavelength, very, very high energy light. But so all of these kinds of electromagnetic radiation are the same beast. They're just different. They're just different wavelengths. They all have the same speed in a vacuum. So the wavelength is the distance from peak to peak or trough to trough. So it's just a length in inches or microns or meters or something like that. Another measure of the different kinds of light is the frequency. So if you're standing in one spot and these things are shooting past you, and you're measuring the voltage going up and down, up and up, and how many peaks do you measure per second? So the wavelength is given a symbol lambda, Lambda, and it's in units of length, like centimeters. The frequency is given the letter nu, and it is in well, it's got to be, so how many of these things are passing us? The way to do that would be something like cycles per second. a lot of times when they write the units for these things, in order to confuse the unwary, they might sort of imply the cycles but not actually write it. And so sometimes you may see it as just per second. And the cycles is kind of like implicit but not really written out there for you. Or sometimes you may see it as seconds to the -1, which just means 1 over seconds. Now, if you know the wavelength of the light and you want to calculate the frequency, so let's imagine these are train cars and you're standing next to the tracks and watching this train go by, and a car goes by every 2 seconds. How do you know? Well, okay, so say you have the frequency, you want to measure the wavelength. They're going past every 2 seconds. How do you know how long the cars are? That would be analogous to going from frequency to wavelength. And the answer is you got to know how fast the train is going, right? Because if they're going past every 2 seconds, but the train is moving incredibly slowly, then maybe the cars are this long. Or if it's going very quickly, then every 2 seconds would be a longer car. So the way to do these kinds of calculations, and this is all about what the lab is going to be next week, is to pay attention to the units. I mean, I could give you formulas that you could measure or you could memorize, the frequency equals the wavelength times that, whatever it is. But that's stupid to try to memorize formulas. You'll never remember that stuff, 2 years from now or whatever. But if you pay attention to the units there, the centimeters and the seconds, it can guide you to the right answer. You don't need to memorize anything. Just construct the answer out of these units, and it will sort of take you by the hand and lead you to where you want to go. And the lab next week is all about following the units to get the answer, because there's lots of different ways that things can be expressed. So let's say we wanted to know what is the wavelength of some light that's passing by. And the units of the wavelength are centimeters. And what we have to start with is the frequency. And so the frequency, let's actually, I already did this to you, this trick of dropping the cycles. Wavelength is actually centimeters per cycle if we want to be explicit. So that's a little clearer now. So we will say centimeters per cycle, and we want to construct that unit out of stuff that we know. So what do we got? We got frequency that has cycles and seconds, and so we need to use that cycles, and we need it to be on the bottom of the fraction. So we're going to start out with that frequency, and we're gonna invert it. So 1 over frequency, and that will now be turn this upside down. The units will be seconds per cycle. So that bottom is good, but the top we've got seconds instead of centimeters, what we want. And we already kind of figured by standing next to the train tracks and kind of thinking about it that we need to know how fast the train is going or the light is going. And so the speed of light in centimeters per second is our ticket here to solving the problem. So we want to have something that has seconds on the bottom and centimeters on the top, so the seconds cancel and leave us with centimeters per cycle like we're looking for, and that's just the speed of light. So it's called the factor label method, and you gotta sort of pay your dues by actually writing out the units. Because you try to do it in your head, you'll get confusing. But I do this to this day. I learned this in high school. It took me a couple weeks to get my head around it, and I still do this all the time because it just leads you to the right answer. So you write out the units and you cancel them, and what you end up with is centimeters per cycle that balances, and there's some numbers, 3 times 10 to the 8th centimeters, 10th centimeters per second, and then you multiply the numbers as it's indicated by this thing that you just did, and it will give you the right answer. So I want to sort of finish up by talking about some other kinds of units that will come up a lot in the lab next week. And you can sort of sling them around and cancel them and manipulate them in the same way, using the same sort of factor label method. So a unit of energy is an easy to understand one, is the calorie. A calorie is how much energy it takes to raise 1 gram of water, raise the temperature of it by 1 degree centigrade. It matters a little bit if the water starts out at high temperature or cold temperature or something. So I think the formal definition is 1 gram of water starting at 25 degrees C or something like that. But it doesn't vary that much. And you can sort of imagine how much energy it would take to warm up. A gram is it's about the size of a raisin. How much it would take to warm that up by 1 degree, that's 1 calorie. So calories are what you read about when you're buying your food. Dietary calories are, by some weird convention, I don't know who came up with this, but a dietary calorie is equal to 1,000 sort of scientific calories. Or equal to 1 kilocalorie. So when you read the label on a candy bar, what you're reading is kilocalories, not calories. And then there's another unit of energy, which is actually sort of the more preferred scientific one. It's totally analogous to calories or kilocalories in the same way that inches and feet and meters and miles are all measuring the same thing, length, and you can convert from one to the other. The unit is joules. And a joule is equal to, 4.2 joules is equal to 1 calorie. So you'll be calculating lots of energies in joules in the lab next week. And then there is a form of unit that will also come up a lot in this class, which is a rate of energy flow. Which is the watt. A watt is 1 joule per second. So it's the rate of energy flowing. So to demonstrate kind of how these units work, I'm going to do a demonstration involving a Reese's peanut butter cup, which is a confection of chocolate and peanut butter, very tasty. And I looked up on the web this morning that one peanut butter cup has 38 calories, just on the nutritional label. Now that is, because it's dietary calories on a nutritional label, it's actually kilocalories. So we'll say, quote cals, 38 kilocalories. And we're going to convert this to joules. So the conversion factor between joules and calories is 4.2. And the way we do it is by, if 4.2 joules equals 1 calorie, then taking a 1 and putting it on top of the other you're just dividing two things that equal each other, so it equals 1. So we can say 1 calorie equals 4.2 joules. 1 calorie equals that, and so we just draw it as this line. And so if this equals that, then you divide them and it equals 0. So you're not changing the answer you're not changing the peanut butter cup by converting it to joules. You're just converting it. And let's say that I'm going to eat that in 1 second, because I want to calculate watts. And watts are joules per second. So I want, what did I do? I did this upside down. How can you let me get away with this? Wake up. So calories on the bottom and 4.2 joules on the top. And see, now the calories can cancel. I had it wrong before. So now we want, for watts, we want joules per second. And so I'm going to eat that thing in 1 second. And if we calculate how many watts of energy that is over that 1 second, the number I get is a large one. So watts, you're familiar with from stereo systems and hair dryers and microwave ovens and things like that. Pretty much the biggest thing you can plug into normal electrical AC lines is a couple thousand watts. So hair dryers, 1,500 watts. Microwave ovens. If you want anything that's an appliance that uses more power than that, you've got to get special wiring, 220 or something like that. So that's kind of like the scale of the electrical. So a hair dryer equals 1,500 watts. So we could use this. So 1,500 watts, and then we'll use the factor label method to convert this to hair dryers. So 1,500 watts is a hair dryer. And so this is power equivalent to 100 hair dryers, all aiming at my head at the same time as I eat this peanut butter cup. Another way to look at this is how much is this going to warm up my head. So I Googled yesterday and discovered that the average human head separated at the third vertebra weighs about 5 kilograms, 5,000 grams. So if we start back from the 38,000 calories, and we say that 1 calorie is able to raise the temperature of 1 gram of water by 1 degree C. And then we got to get rid of the grams here because we just want how much my head is going to warm up. My head, assuming I am an average human, is 5,000 grams. So the grams go away, calories are gone, so we're left with degrees C. And this thing has enough energy to warm up my head by 7 degrees C, which is about 12 degrees Fahrenheit. So normal body temperature 98.6 plus 12 gives me a body temperature, a head temperature of 110 degrees, which will instantly kill me, of course. So here we go. Now, the reason why I'm not dead is because this term right here, chewing it doesn't actually burn, it doesn't actually release all of the energy. The energy will eventually make it to my stomach as soon as I finish swallowing here, and it will take a few hours to burn. So I kind of tricked you a little bit there, but anyway, it sort of demonstrates, while allowing me a nice treat, how you can sort of use these units. So great, I will see you on Monday.